In case you are speaking something, you are not audible, or probably you are on mute.
Sorry, can you hear me now?
Yes, yes, you are audible.
Okay, thank you. Okay, so what is a matrix? Matrix means it contains m by n many elements in some order like this. There are m by n, m times n many elements, and uh, we are storing those data in this format. This is called matrix, and usually those elements are taken from real number, but we can take the matrix. So this is denoted by m times n over real number. But those entries can be taken from complex number or any other field. For example, Z2, Z3 like this. Now we already know about matrix addition multiplication. So matrix additions are done by pointwise addition, that is 1 2 3 4, and there is another matrix 0 1 1 0. Then we add those two elements, that is 1 2 and 1, which will be 3, and this element 3 plus 1 will be 4, 4 plus 0 will be 4, in this way. And matrix multiplication are done by row times column. So first row times first column, this will give me this element, first row times second column. So this will give me 1/2 element like this. Then second row times first, second row times second. Okay. So this is how we do matrix multiplication and matrix addition. There is also another operation which is called scalar multiplication. So for example, if we want to multiply the matrix 1 2 3 4 with 2, then we will multiply by pointwise. So first 1/1 element, this will be 2 times 1. Then 1/2 element, that will be 2 times 2, then 2 times 3, 2 times 4. So that is how we do matrix addition multiplication and matrix multiplication with a scalar. Okay. Now we know that to solve linear equation, we need to know row reduction. So what is row reduction? Given a matrix M or A, suppose A is some matrix and it has some row R1, R2 up to Rn. So those are rows. This is this rows, this is denoted by R1. Second row, this is denoted by R2 up to Rn. So there are n many rows. Now what will be row reduction? We can perform some operation. For example, we can exchange any two row. So suppose first two rows are exchanged. Let me denote the operation or denote it by this exchange notation. R1 and R2, those are exchanged. So it will look like, okay. So it will look like R2, R1, and everything remain fixed. Moreover, we can also do scalar multiplication. So we can multiply any row. For example, Rm, multiply Rm with some constant C. So C times Rm. Then it will look like R2, R1, and the mth row, it will be multiplied by C. So C times Rm. And we also can add one row with another by some scaling. So Ri plus C times Rj. So Ri can be changed to this. Okay. So ith position, everything will fix, but ith position, it becomes Ri plus C times Rj. So those are some row operations, and uh, what will we do? We perform those kind of operation, finitely many operations, and finally we get some matrix which is simpler. So what does this mean? Simpler means it it is called row reduced matrix. Row reduced matrix. So row reduced matrix means, let me give an example, then I'll explain. So it will look like something like this, and there will be lots of zeros. That is the main thing. 0 0 0 1 0 0 1. So this is an example of row reduced matrix. So row reduced means if the leading entry, that will be 1. So you can see that whatever row you take, for example, if you choose row 2, then first non-zero entry is 1. Okay, this is one of the condition, and another conditions is if a column contains this leading one means this first non-zero entry, which is 1, then all the other entries of that column will be 0. For example, if we choose this, then it contains this leading one, because if you see third row, then 1 is the first non-zero entry which appears in column 2. So all the other entries should be 0. So this is how row reduced matrix is defined. And there is another kind of matrix which is called row echelon form, row reduced echelon form, row reduced echelon form. In short, it is denoted by RREF. In this case, those leading entries, for example, one, it is a leading entry, and this one is leading entry of row 2, and this is for row 4. So those entries are in a ascending order, strictly ascending order. Means the position of the column position of this leading entry. For example, it appears in column 1, column 2, it appears in column 3, but it appears in column 4. So we need to exchange the rows such that it will appear in a order. So let me write it so that it will be clear. So we need to send the first row which contains only zeros to the last. So it becomes 0 0 0 0 0. And now the first row, so first leading entry appears in the third row. So we need to put the third row in first. So 0 1 0 0 0. And then the next leading entry appears in row 4. So we need to put row 4 in the second place. So 0 0 1 0 minus 2. Then another one will be 0 0 0 1 0. So this is called row reduced echelon form. Now you can see that it it is almost row reduced matrix, but those leading entries appear in a certain order. Okay, so this is how the form look like. So why do we use those kind of row reduction? Let us see some example and the reason behind this. So let us consider the first question. In question number 1, the given matrix is A, which is 14010. The matrix is given by this. So there are 4 rows and 1 2 3 4 5 columns, 4 by 5 matrix. Now let P denote elementary matrix which replaces 2 by row 2 minus 2 times row 1. Okay, so what we are doing, we are given a matrix A, we are applying some row operation. So we are changing the row 2 by row 2 minus 2 times R1, and row 3 by row 3 minus row times R1. So instead of performing on A, we can perform on the identity matrix, because we need to see uh, the matrix P. We need to find the matrix P such that P times A equal to this new matrix. Okay, what is happened after the operation? So we are doing this operation on A. So after operating by those, we are getting some new matrix. Okay, so we need to find this matrix. So this is equivalent to saying multiply some elementary matrix and get A1. So we need to find this elementary matrix P. Okay, so how can we find? We'll take this identity matrix, 4 by 4 identity matrix, because there are 4 rows. So it is 1 0 0 0 0 1 0 0. Now R2 minus 2 times R1. What will be that? So first row remain fixed. Second row becomes this minus the first 2 times first row. So it is minus 2 0 uh, minus 2 1 0 0, and R3 minus R1. So it becomes minus 1 0 1 0 0 0. So now we can see this is same as uh, minus 2 minus 1. So this is same as option D. Okay, so this is how we can perform row operation. Here we have performed the row operation on I, identity matrix, I 4 by 4. Okay, the same operation on identity matrix. Now question 2. So consider the matrix A in question 1, the matrix B such that A and B are row equivalent. We need to find matrix B which is row equivalent to this matrix, this given matrix. Okay, so let me write the matrix. Okay, so the given matrix was that 1 4 0 1 0, then 2 1 0 minus 1 0, and then 1 8 0 2 0 0 1 2 0 1. So we are doing those two operations, R2 minus 2 times R1. So subtract 2 times row 1 from the second row and subtract row 1 from the third row. Those two operations we are performing. So first row remains same. It is 1 4 0 1 0. Now the second row becomes, so R2 minus 2 R1. So this 2 minus 2, it get cancelled. So we'll get 0. 1 minus 8. So it becomes minus 7. Then 0 minus 1 and minus 2, it becomes minus 3. Then 0. So R3 minus R1. So it is 1 minus 1, which is 0. Similarly 8 minus 4, it is 4. 0 minus 0 0. 2 minus 1 1, and 0, and everything 0 1 2 0 1. Okay, so this should be the answer. Okay, so copy. this is not the answer. Let us check other options. Now we can see that this is exactly option B, right? One, no, not option B. It is 0, 1, 2, 0, 1. It is option C. So C is the correct answer. So this is how we can perform row operation to reduce the given matrix. Similarly, we can perform others row operation to get row echelon form or row reduced echelon form. So successively apply and first. So here we have what we have done. We just okay. So the first non-zero entries, those are removed by this row 1 using row 1 because row 1 contains a non-zero entry. Then what we can do now, this minus 7, if we consider a second row, then just multiply it by minus 1 by 7 so that it becomes 1, and we can subtract this second row from other rows so that those element becomes 0. Okay, similarly after that the next step will be using other rows. Okay, so this is how we successively get a row reduced echelon form. Okay, let me complete this example. Okay, so we need to find row reduced echelon form of this matrix. So let me do it. Okay, so this was the matrix after first operation. Given matrix was A, and we have just applied these two operations. Now what are we saying is we can choose any row particular, so we can probably this is the best choice because it is already the first entry is already 1, so we can exchange the first r1 and r4. Okay, so sorry, r2 and r4. First row remain same 14010, and then this will put the fourth row in the second position, so it becomes 01201, and then third row remain same 04010, and finally we'll get 0 minus 7 0 minus 3 0. Okay, now we need to subtract from other rows because it has leading one, the second row has leading one, so we need to subtract this row 2 from this row 1. So what will be the subtraction? We just multiply it 4 times and then subtract it. So I want to say r1 minus 4 times row 2, so that the second 4 these get cancelled. Okay, it will becomes 4 minus 4, so it is 0, right? So the second row is fixed, we will not change the second row 0 1 2 0 1. So what we have done, it is r1 minus 4 times r2. So the next entry is 0, 0 minus 8, then 1 minus 0, 0 minus 4. Now again the similar thing happens here. There is another 4, so we'll perform r3 minus 4 times r2. So it becomes 0 0, and then 0 minus 4. Sorry, minus 8, 0 minus 8, and 1 minus 0, 0 minus 4. Okay, then what we'll do, we perform this operation R4 and add 7 times R2, so that this minus 7 get cancelled, right? It becomes 0. So what will be the result? 0 0. Then 7 times row 2, which is 14 plus 0 0. 14 plus 0 means 14. Then minus 3 and 7. Okay. Now our target is third column. So those two are already done. First, this row and this row is done. So what we can do, we just multiply this row by 1/8, so that this becomes 1. First leading entry becomes 1. So first two rows are fixed: 1 0 minus 8 1 4 0 1 2 0 1 0 0. So minus 1 time 1 by 8 times R3, minus 1 by 8 minus 4 by minus 8, which is half, and this is also same, 14 minus 3 7. So our job is to remove all the other non-zero entries for this leading one. Okay, so we want to remove, okay, we want to remove all those minus 8 2 and 14. Okay, so what will be the operation? It is R1 plus 8 times R3, then R2 minus 2 R3, and R3 minus 14 R3. Then it will become, so R1 plus 8 R3 means this 8 plus minus 8 becomes 0, 1 0 0. Then minus 1 plus 1, which is again 0. Then 4 plus 4, which is 8. After that, R2 minus 2 R1. Okay, so it is 0 1. 2 minus 2 becomes 0. Now plus 1 4, and then minus 1 1 minus 1, it becomes 0, and this remain fixed: 0 0 1 minus 1 by 8 and half. After that, it is 0 0. 14 minus 14 becomes 0, minus 3, and minus 14 into minus 1 by 8, so plus 14 by 8. Okay, so this is same as minus 10 by 8, so minus 5 by 4, and then 7 minus 14, which is minus 7. So another reduction is possible. What we can do, we just multiply this. First, we can multiply this with 4 by 5, minus 4 by 5 times R4, so that the leading entry becomes 1. So then this will becomes 1 1 1 1, right? And we need to cancel all those above entries, so 0 0 0, and there will be some elements here, right? So you can check those things. Let me complete it because it is almost done. So what we can do is 0 1 4 minus 1 8 and 8 0 half minus 7. So it is R2 minus 1 4 r 1 4 times r4 and r3 plus 1 8 times r4. So this becomes, first part will becomes identity matrix. So let me put a big identity 4 by 4 order, and there is another column which we need to compute. So first row we have not performed anything. On the second row, r2 minus 1 4 r 1 4 times r4. So 0, there is minus 7, 7 by 4. Then r3 plus 1 8. So r3 means half plus 1 8 times minus 7. So minus 7 by 8. Okay. So this is minus 3 by 8 and minus 7. So this is how the row reduced form will look like. Uh, okay, maybe I have done some mistakes. The answer should be D. So you may do it again. I don't know where is the mistake, but you can check. There will be some mistake, some calculation mistake, but you should get this answer. Identity, and there will be 0 0 half comma 0. Okay. Sorry about this. So okay, let me skip this question and now vector space. We'll discuss vector space. So what is vector space? Sorry about those calculation mistakes. So vector space means it is a set V and there are two operations. V is equipped with two operation, binary operation plus and another is dot. The operation will, there should be another set which is called field, scalar field. So V plus dot is a vector space over scalar field A. This is called field. So what are some example of fields? You already know fields are, for example, are real number, rational number, or complex number, where you can both perform addition and multiplication. You can multiply any two rational number, any two scalar, any two complex number. So those plus, there are two operation plus and multiplication. Those satisfy some properties, commutativity, associativity, those kind of properties, and inverse. Every element has inverse. Okay, so if satisfy those kind of properties, it is called field. So the common examples are real number, rational number, complex number, and some ZP. Okay, what is ZP? ZP means the elements are will be of this form 0 1 2 up to p minus 1. That is, we are taking integer modulo p, so p becomes 0. It is like dialing of, so 0 1 2, and after p it becomes again 0, p equal to 0. So we are taking integers modulo p. So this is also a field, example of field. P is prime, otherwise it is not a field. Now what is the definition of vector space? It means there are two operations. One operation is over v, so from v to v we'll get an element of v, and there is another operation. So if we take an element from scalar field a, another element from v, then if we do scalar multiplication we'll get an element from v. So that means what we are doing, if we take any two element v1 v2, we'll get an element v1 plus v2, and if we take some element c comma v, we'll get c times v. And those two operations has some properties. So v plus is an abelian group. So I'll explain the meaning of abelian group such that and there is some property with some properties related to the scalar multiplication. So there exists an element 1 which is identity element from the scalar field f, such that 1 times v equal to v. This is true for all v belongs to v. And there are other distributive properties. For example, if you take any scalar c and any two vector from vector space c is from the scalar field, for all those things we have c times v plus w is same as c times v plus c times w. Similarly, there will be another symmetrical distributive property. If we vary c1 c2 and we perform the scalar multiplication, this is same as c1v plus c2. And there is associativity kind of property, c1 times c2. If we first multiply and then do scalar multiplication with v, this is same as first multiply with v and then multiply with c1. So it is similar to those group. You already probably were familiar with group theory. So in group theory there is only one operation, only this kind of addition or some kind of product type of operation. But here, instead of one operation, there is another multiplication operation, so which relates this field and this vector space. Not relating, but there is some operation like this, some binary operation, which satisfy this kind of property. And another thing is that what is the meaning of abelian group? Abelian group means those kind of group theoretic property. So there is associativity property. So associativity means v1 plus v2, and then if we again add v3, this is same as first add v2 v3 and then add v1. Okay, and there is called zero additive identity or zero. So it means if you add with zero, this give me the same element. Okay, there is additive inverse denoted by minus. So for every v, there exists some minus v belongs to v, such that v, if we add with minus v, we'll get 0. Or first add minus v and v equal to 0. And there is a there is another property, commutativity, or it is called, because of this it is called Abelian group, this commutativity property. It means if we add in this way v plus d w or w plus v, those order does not matter, those are same for all v w belongs to the vector space v. So instead of looking at those properties, it is easier to consider some example. So how the most natural example will be real number. This is a vector space over the field R. R itself is a field, we have already said. So let me say what is the meaning of field explicitly. Field means, again, there are two kind of operation, f with addition and multiplication, but instead of f cross v to v, the multiplication here it maps f times f to v. Okay, those corresponding to two element will get one element, such that f comma plus is abelian group, and if we remove the element 0, then this is denoted by f star or f cross. So f star comma dot is also another abelian group. So there is multiplication and addition, both are both will be commutative, and there is also some relation connecting those two, addition and multiplication, like this, some distributive property or and something, some associative property like this. So plus extra those properties, plus relation between plus and dot. Okay, there are some relation. So R is a vector space over the field R. Okay, and so what will be the addition and multiplication? So we already know we can add any two element given x and y from R. We can always add two element x plus y, and we can also multiply any two element x times y, and we can see that this this the real number, the set of real number forms a field. That is, we can check all those property. Real number satisfies this kind of abelian group properties. Associate addition is associative. There is some 0. There is additive inverse, and this addition is also commutative. Similarly, we can check those kind of properties, multiplication. So this is one example, and similarly another example will be complex number addition and multiplication over C. Okay, but if it is a field over C, then it is also a field over R, right? Because instead of multiplying with some element of C, element of complex number, so some C times X plus IY, we are multiplying it with some element from R. But R is a special case of, R is a subset of C. So it is a field over C will also suggest that it will be a field over real number. It's real number. Okay. So what are so those are very basic example, But the main key example will be this. Take n tuples Rn. So Rn consists the element like this: x1, x2 up to xn, such that all those xi belongs to R. Okay, it is just product of n set, and all those n sets are real number itself, and there are addition and multiplication. How can we define addition operation? How can we add n tuples? So let us consider R2, and we can do the same thing for two element x1 x2 and y1 y2. We can add those two elements. So suppose v is x1 x2, another element w is y1 y2. Then v plus w, this is defined by point wise addition, coordinate wise. So x1 plus y1, and the second will be x2 plus y2. This is what we really do in vector. That is, in vector calculus also we can add those kind of thing. So suppose there is one element 1 2 comma 1, this represented by the vector v, and suppose there is another element 1 comma 1 like this. Then what will be the sum of those two elements? We just we perform this kind of thing. So from 2 comma 1 we start this 1 comma 1 vector, we just shift the origin so that their sum becomes this 3 comma 2. So we are doing nothing but point-wise addition, coordinate-wise addition. Similarly, what will be multiplication by some scalar? For example, 3 belongs to real number, so we can multiply 3 times this 2 comma 1. Then this vector will get stretched. So we just extend. So it will become 1 2 3 4 5 6 6 comma 3 1 2 3. So this will be the resulting thing. So this is 3 times p, the new vector. Okay, this red one from origin, it starts from origin and goes to this 3 6 comma 3. So again we are doing coordinate wise multiplication. So this is the main most important example here, and very useful example also. This can be done for any dimension. It is only done in 2 dimension, but this generalizes to any n dimension. So here x1 up to xn, and suppose there is another element y1 up to yn, then their addition will be given by this pointwise x1 plus y1, then x2 plus y2 up to xn plus yn. Okay, similarly, if c belongs to some scalar, c is a scalar, then c times the vector x1 x2 up to xn, this is same as cx1 cx2 up to cxn. So this is how we can define scalar multiplication and addition and scalar multiplication. Okay, we can check all those properties. We can check those kind of distributive, associative, or this property, abelian group properties. All of those properties will be satisfied by this vector space Rn over. So we have defined Rn with addition operation and scalar multiplication operation. This is a vector space over R, the field R, real number. Okay. So there are also more examples. Instead of considering these n tuples, we can consider polynomial, n degree polynomial whose coefficients are taken from real number. So it will look like some f where fx, which is same as, instead of f, let me write fx a0 x to the power n plus a1 x to the power n minus 1 up to an. Okay, such that all those AIs belongs to real. So can we add any two polynomial? Yes, the same procedure. So suppose one polynomial. So how? Let me give an example. 1 plus 2x, or x square plus 2x plus 1. This is one polynomial. Another polynomial is 3x plus 1. Those are two vectors. So we can add by those degree wise. If two element has same degree, then we can add. So 3x and 2x, those two will be added. We'll get 5x. 1 and 1, those two will be added. We'll get 2. But there is no element, no x squared term in the second element. So x squared plus 0 is x squared. So note that those two are not very different. So we can again, this is not something new, because this x squared 2x plus 1 we can write in this coordinate notation, right, as a tuple, because 3x plus 1 also it can be written as 0 3 1. So and if we add those two elements, sorry, 1 to 1, so it becomes 1 5 1, 1 5 2, which represent this element. So that is why I was saying that this is the main example, this Rn. Okay, because all those vector space you can write any, if you take any vector space, it always, you can always write it as a coordinate. So we'll see later why this is the case. This is an important fact now. And similarly, we can do multiplication by simply, we know how we can multiply it with a polynomial. And we can also consider any m by n matrix with addition and multiplication, as we have discussed in the first few moment. So for example, let us consider m2 by 2. If we consider one vector abcd, another vector efgh, then their addition will be entry wise again. So it will become a plus e, b plus f, c plus g, and d plus h. Now if we take, so we are considering the matrices over real number, so all those entries are coming from real number. Now if we multiply this abcd with some scalar c is already there, so I am taking k. K belongs to real number. Then this is same as ka, kb. Again, pointwise multiplication. So again, we can check that this is a vector space. All those properties are satisfied by these examples. Okay, so let us let me give another definition. So up to now we have discussed vector spaces. Now let us discuss subspaces. So consider this xy plane or R2, and now if we consider some relation, that is, suppose there is a relation like this, 2x plus or x plus y equal to 0, then this relation gives me this line, right? Something like this. All the elements will look like x comma minus x. So now if we consider this line, then all those elements, so the new vectors, let me denote this line by some w. So w can be written as all x comma y belongs to R2, and there is some relation which is x plus y equal to 0. Okay, then we can check that w itself is a vector space. Okay, so how we can see that? So if we take any two element, suppose one element x1 y1, or instead of xy let me denote it by x1 x2, it will be easier. This notation is easier to deal with, convention. So suppose x1 x2, this is one vector v belongs to w, and another vector, this is v1, another vector is v2, which is y1 y2. This is also belongs to w. So if we take any two element, one element will be like this and another element is something like this, then we can see their sum is also belongs to the line. Graphically it is easier to see. If we take any two vector from this line, then their addition also belongs to this line. So because they are in the same direction, right? And we can also check it by this mathematically abstract, in an abstract way. So those two belongs to w means, first one belongs to w means x1 plus x2 equal to 0. The second one belongs to w means y1 plus y2 equal to 0, right? Now what does this mean? This means, now let us see that if the addition x1 plus y1, addition of these two vectors, which is given by x1 plus y1 and x2 plus y2, the question is their addition also belongs to w? This is the question. So let us check. So if to see if this belongs to w or not, we need to see that these properties are satisfied by this element. So now the second component is x2 plus y2 and the first component is x1 plus y1. So we need to see if their sum is 0 or not. So again, we know that in real number there is commutativity, associativity, those kind of thing. So we don't care about this bracket, and we can add it by any way, whatever you want. So x1 plus x2, this becomes 0, y1 plus y2 also becomes 0. So their sum is also 0. Okay. Similarly, if we stretch any vector that is scaling by some c, so c belongs to real number, then c times v, it will look like c x comma cy, c x1 cx2, right? Now again, the sum of the components cx1 plus cx2, this is same as c times x1 plus x2, but x1 plus x2 is 0, so by star we are getting this is equal to 0. Therefore their addition and their scalar multiplication belongs to the same w. So we say this belongs to w, this is correct. Therefore we say that w is closed under addition, and here c times v, here we are getting c times v belongs to w. Therefore we will say that w is closed under this multiplication. Okay, someone is. Okay. So w is closed under addition and scalar multiplication. Now it is an interesting exercise. You can check that if those two properties are satisfied, then all the others properties, all those properties, those will be also satisfied by w. So if you take addition and multiplication, those will be satisfied. Those will be a particular case of these previous properties. V satisfies these properties. Now W is a subset of V. So W, in particular, W will also satisfy those properties. Okay. So W becomes a vector space because of those two properties. It is closed under addition and closed under multiplication, scalar multiplication. Sorry, closed under scalar multiplication. Therefore, W will become a new vector space. But W is also a subset of V. Therefore, it is called W is a subspace of V. So, how we can define a subspace? Subspace means okay. Subspace given a vector space V, let W is a subset of V. W is a subset of a vector space. Vector space V is a vector space over V is a vector space over F. If W is also a vector space, over F, then W is called a subspace. Okay. So here we are meaning that all those operations are preserved. That is, whatever operation was given for V, we are taking the same operation because W is a subset. So we can perform the same addition and same multiplication. W plus dot, we should write. So V plus dot. There are, okay. So how can we check if something is a subspace or not? So we only need to check that W is closed under addition and closed under scalar multiplication. So what does this mean? So if W1 comma W2 belongs to W, we need to check this will, is this imply W1 plus W2 belongs to W. We need to check that. If this is true, then the first closed under addition, this property is satisfied. And another property, if C belongs to scalar field and W belongs to capital W, then we need to check C times W also belongs to W. So we need to check those two properties. If those two properties holds, then we'll say W is a subspace. Okay, let us solve some example. So in the first example, we are considering P3R. P3R means polynomials up to degree 3. Polynomials of degree less or equal to 3. Now W is a subspace of, let W be the subspace of P3X consisting of elements like this. Okay, elements will look like this. Then Px can take the form. So we need to find the condition such that W is a subspace. Okay. Uh, Here I should also mention that 0 always belongs to the subspace. Observation. Okay. Otherwise, that is, in the definition of vector space, there always be an additive identity, that is 0. This is an important. So before checking, we always check if 0 belongs to W or not. If 0 does not belong to W, we will not check, because it will not never be a vector space. Okay. So note that in P3X, the addition is already, we know how we can add, just adding those coefficients, and we also know how we can multiply all those coefficients with that fixed scalar. So if we consider the first condition, then it is clear that 0 belongs to that subspace. So we are finding the conditions Px belongs to this P3X and some condition, that is condition A, B or C, D, condition for which W is a subspace. So if we take the first condition, that is we are considering A0 x cube plus A3 up to A3 such that the first condition says A0 greater equal to 0. Will it be a vector space? What will be the problem? So we can see that let us take A0 equal to 1. Okay. So let us consider this particular example. Let Px equal to x cube. Then it is clear that this this polynomial belongs to W1, right? But if we take scalar multiplication, so note that -1 also belongs to real number, and if we take c equal to -1, so c times px, what will be that? C times the vector px, it is -1 times x cube, which is minus x cube. Now will it belongs to W1? So clearly you can see that the coefficient of x cube is negative, which violates this condition, because it is already given that A0 should be greater equal to 0. So this does not belongs to W1, right? Therefore, this is not a vector space. Now what about the second one? A2 equal to I times iota times A1. So will it be a vector space? So again you can see that if A2 equal to I times A1, iota times A1, this condition cannot be satisfied because we are considering vector space over real number. But here the relation is coming from complex number. So A2 equal to I times A1. For example, if we take A1 equal to 1, then A2 becomes 2. A2 becomes iota. So for example, what is happening? There are some element like this: x cube plus 1 times x square. Now, sorry. So let us take A2 equal to 1. So there will be some x plus then A1 will becomes, sorry, A1 equal to 1. If we take A1 equal to 1, then we will get, this will imply A2 equal to iota. So it is x squared plus A2x. A2x means iota x. So this cannot, this element satisfies this condition, but this cannot belongs to W because W must be a subspace of P3R. W is a subspace of P3. Sorry, this should be denoted by P3R. So there is no such element. No element will satisfy this relation. A2 equal to I times iota times A1. Okay, but we can say because uh, there there will be only one element which satisfies this relation. The element is 0. So 0 is the only element from P3R which satisfies this condition. Okay, so in this way we can say, but this is, if we trying to define by this condition, then this is not possible because there are some elements uh, which does not belongs to P3R. So the conclusion is this is not a correct answer. Now what about A3 is rational, this condition? So instead of A0 equal greater equal to 0, we are now replacing it by A3 equal to rational. Now what will be the problem? So in this case, if we consider the third, that is W3, this corresponding to this vector space, then we can say that 1 belongs to W3, or let me take x plus 1. This belongs to W3. But the problem is, yes, there is some question.
Yes, can I ask a question, sir, please?
Yes, definitely.
So basically, what we are doing here, we are looking for a periodic S of x, like via the axiom of a specification, where S of x is closed under linear combination, right?
Exactly. It closed under linear combination, addition and scalar multiplication.
Yes. Thank you so much.
Yeah. So I am saying that we are taking this Px from polynomial which satisfies this condition. This one, or corresponding to C, I am denoting it by W3, the set. So you can see x plus 1 belongs to W3 because A3, in this case, A3 is 1, which is rational. Sorry, not this. A3 is rational. So this belongs to W. Instead of W3, let me denote it by W4. But if we multiply with some irrational number, so root 2 belongs to real number. So if we multiply this vector with root 2 times v is equal to root 2x plus root 2. So now we can see that root 2, this does not belong to, does not satisfy this condition. This is not. So A3 term, this is not rational. So here, if we take the condition D, then that corresponding set W4 is not closed under scalar multiplication, right? So this is also not a vector space. So here it was not closed under scalar multiplication. It is in option B. It is not even a subspace, and here again it is not closed under scalar multiplication. Now for option C, we can check that this is a subspace. So let us check this condition. A3 equal to A1 plus alpha square A2. Alpha is a fixed real number. Okay. We are considering all those polynomials. Px belongs to P3 polynomial over R. So Px will look like A0 plus A0 x cube up to A1. Sorry, A3. So there is a relation between those the coefficient of those polynomials given by this relation. Now let Px, so denote this set by W3. So let Px belongs to W3 and another polynomial Qx belongs to W3. Or let me denote it by P0 dash, P dash x. So Px was given by A0 x cube plus A1 x square up to A3, and it is A0 dash x cube up to A3 dash. So what does this mean? This means there is some relation like this: A3 equal to A1 plus alpha square A2. And similarly, from here we are getting A3 dash equal to A1 dash plus alpha square A2 dash. Sorry, just a minute. Okay, so there are two such relations. From here we can see that what will be the addition. So instead of, sorry, it is not filling. Yeah. So we need to check that their addition and scalar multiplication, those two will satisfy this relation. So I was telling that instead of performing those two operations individually, we can perform in this way. So instead of checking in two different ways, we can simply, sorry, instead of checking those two individual relation, we can simply check this relation, that linear combination CW1 plus C1W1 plus C2W2 belongs to W. This is for all C1, C2 belongs to F, and W1, W2 belongs to W. So we can directly check this linear combination instead of checking those two different conditions. those two condition is equivalent to this. So let me check the condition. So let us take C. Let C belongs to scalar field R. Okay, C1 and C2. C1, C2. Then C1 times this Px plus C2 times P dash X. This will be same as C1 A0 plus C2 A0 dash X cube plus again it will go similarly C1 A1 plus C2 A2 A0 dash sorry A1 X squared. So this will be the addition of those two polynomial. So this is the linear. This is also called linear combination. Now, if we see this linear combination, we need to check if this relation is satisfied or not. So, what is A3? In our case, this kind of relation is satisfied or not, we need to check. So, let me denote it by some new name. So, let me denote it by some k1 x k0 x cube plus k1 x squared plus k2x plus k3. So this is equal to this. So we need to prove those two are same. That is, if we take k1 plus alpha square k2, we need to check this is same as k3. We need to prove this thing. So what is k1 plus alpha square k2? This is our k1, coefficient of x squared, and k2 is coefficient of x. This is k2. So c1 a1 plus c2 a1 dash, and this is plus alpha square k2. K2 means c1 a2 plus c2 a2 dash. So let me denote it by equation 1, equation 2. Then we can simply take c1, and this is a1 plus alpha square a2 plus c2, then a1 dash plus alpha square a2 dash. Then the first, by equation 1, this is same as a3. So c1 a3, and by equation 2, equation 1, and here equation 2, if we use equation 2, this becomes c2 times a3 dash. So sorry, c1 times and this plus c2 times, yes. So this is nothing but, just see that this is actually k2, right? No, sorry, not k2, but it is actually this element. This element, sorry, k3. So this is actually same as k3. K3 equal to this element. So from here it is clear that therefore this W3, this set is closed under addition and scalar multiplication. Okay, so therefore W3 is a subspace of P3x. P3, or whatever you said, P3x, if the x is denoted for this, x is denoted as variable. So this is the correct answer. Okay, you can check this question that here we are considering n tuples and there are some relation like this, but I am skipping this question. Okay. And we need to check if that is a subspace or not. Sorry, I think there is some. Okay. So we need to see which condition will give me a subspace of n by n of the vector space consisting n by n matrices over real number. So the first condition says, let me denote the set obtained by the first condition. So W1 consists of all those n by n matrices. A belongs to n by n such that a square equal to a plus I. So will it be a subspace of the vector space V? So note that if we take the element 0, 0 which is, it will look like all those elements are 0. This is the 0 element of the vector space. Then is it true that 0 square is same as 0 plus I? 0 square is 0, but 0 plus I will give me identity. So 0 square is 0, which is not same as identity, which is 0 plus I. So from here it is clear that 0 does not belong to W1. Therefore, W1 is not a subspace. What about the second? So A is false. This will not give me a subspace. All those elements, all those matrices A which satisfies AQ equal to A. So W2 equal to all those matrices which satisfies this equation AQ equal to A. So 0 belongs to this W2. This is clear. This is not necessary to check, but we always should check this condition first because it will immediately discard that condition, whatever we have seen in this case W1. So 0 belongs to W2, it is okay. Now this is not true. Let us see why this is not true. So it says AQ equal to A, but if we take scalar multiplication CA, then CAQ will be CQAQ, and AQ equal to A will give me CQ times A. But what should we get? We are taking cube of CA. So our vector is V, what we are considering, we are taking BQ. Let B equal to CA, and we are taking BQ. So we should get B, right? But B is same as C times A. So is it same? CA is same as C cube A. This is not true, right? So what will be a counter example? From here you can construct lots of counter examples. So take identity. So identity belongs to W2. Why? Because since identity cube is same as identity. But if we take 2 times identity, so take this new matrix A equal to 2 times identity. 2 is a scalar from real number. So this should belongs to W2. But what is happening? If we take A cube, this is same as 8 times I, which is 8I. But this is not equal to A. Therefore, though I belongs to W2, the scalar multiplication 2 times I does not belong to W because of this. So this is not true actually. In this case, this is not true. Okay. Therefore, W2 is not closed under scalar multiplication, which implies W2 is not a subspace. Subspace of V, of W or V, whatever is given. So this is also not a subspace. Now, what about D, the set of all invertible matrices? Again, you can see that 0 is not invertible. So 0 does not belong to this set. So D is also false. So the only remaining thing which is need to be checked is A commutes with B up to some negative sign. So this is true because let us see why this is true. W3 equal to all those elements such that AB equal to minus BA. B is a fixed matrix. So let A1, A2 are two elements from W3. So we need to check their scalar combination also belongs to W2, W3. C1, C2 belongs to the scalar field real number. So we need to check their linear combination C1 A1 plus C2 A2. This belongs to the W3 or not. So that is same as checking how is the scalar multiplication commutative up to sign or not. So this is same as C1 times A1B plus C2 times A2. Now note that A1 belongs to W3. So A1B is same as minus BA1. This is true because A1 belongs to W3. Now what about this one? A2 times B. So if we try to add, this is again, since A2 belongs to W3, this is same as minus B times A2. Now we can take this common. So this is same as minus of C1. So we can take B common, minus B times C1A1 plus C2A2. So the linear combination satisfies this relation star. Therefore, linear combination satisfies star. In particular, addition and scalar multiplication both will satisfy the condition star. Therefore, this is closed under addition and scalar multiplication. Hence, W3 is a subspace. of P. So this is the only correct answer. Similarly, you can check the previous question, and there is another kind of question we should see. So let me consider this question. W is spanned by this kind of vectors. There are three vectors. So let me put. So what is the meaning of spanned by some vectors? So let V1 up to Vn are n vectors from vector space V. Then the spanning set, let me denote it by span V1 up to Vn. Those are linear combination of those elements. So linear combination means there are some scalar and addition like this. Scalar multiplication and addition Cn Vn. So such that those Ci are taken from field F. So this is the definition of scalar multiplication. Okay. So this is the definition of spanning set or span of some vectors v1, v2 up to v3. Here we have three vectors. We need to see what will be the spanning set. So instead of considering this example, let me consider some simple example, because there are 4 coordinates, so I have to work more, but let me consider some simple example. So let v equal to r3 with scalar addition and multiplication, and we are considering three or two vector. For example, let us consider two vector. v1 equal to 1 2 3 and v2 will be 0 1 2. Okay, so what is happening graphically? Graphically we are 3 dimension we can draw. So we are also already taking two vectors, one vector corresponding to one vector 1 2 3 means it will look like 1 then 2. So this is x y z. Let me write. So 1 then 2 up and then 3 here. So one vector will look like this, and another vector will, let me draw any arbitrary. Then what does this mean by spanning set of v1 v2? Span v1 v2. This means the linear combination of those two vectors. What will be the linear combination of all those vectors? So if we scale the vector v1, suppose this is v1, this is v2. If we scale v1, then we'll get the whole line like this. If we scale v2, then we'll get the whole line along the direction along v2. So their linear combination actually represents a plane. For example, if we add v1 v2, we'll get some element like this, some element v1 plus v2. This will give me some v1 plus v2. So all the elements in the plane can be written as linear combination of v1 v2. So linear combination represents this plane actually. The plane which contains both v1 v2. Okay. But how can we write mathematically? So it means it will be some c1 times v1 plus c2 times v2. such that C1, C2 both are scalar. So C1 times B1 means C1, comma 2C2 plus 3C3 and C2 times B2 means 0C2 plus 2C2, 2C3. Ci belongs to R. Sorry, there is only one C1. So this is C1, this is also C1. So their linear combination is same as C1 plus 2 C1 plus C2 plus 3 C1 plus 2 C2. Sorry, extremely sorry. So this will be the linear combination of those two vectors. And this will generate a plane like this. But the interesting thing is now the issue is it is hard to see if what are the elements of this plane or what are the element of this spanning set. But interestingly, we can always check if something belongs to spanning set or not. So what will be the way to check? The question is 3 1 comma 2. This belongs to span, let me denote it by, or okay, span v1 v2. This belongs to spanning set of v1 v2 or not. So let us check. So what will be, so let me say the general way to solve this kind of problem. So instead of v, let us consider b1 b2 b3, a general element. b1 b2 b3 belongs to this spanning set or not. So let v, instead of v, let us consider this. Okay, so this belongs to spanning set. This will imply the C1 will be this B1, 2C1 plus C2 will be B2, and 3C1 plus 2C2 will be B3. So if V belongs to the spanning set, so let me denote it by W. This is also a vector space, you can prove. If V belongs to W, then we already know W will contains the element like this. So the first component will look like C1, the second component will look like 2C1 plus C2, the third component will look like this. So then those relation will hold. This relation will hold. So this has a solution. So we need to check if this has a solution or not. Okay. So how can we check? One easy way is like this, putting in a matrix. So first equation means it is 1 0 0 b1. The second equation is 2 1 0 b2. In this case it is easy, but for the most general case I am writing how we can check in. So sorry, there are two things, 3 2 and 1 b3. So b1 b2 b3 belongs to the solution. That means there are some combination of those two things which give me b1 b2 b3. So I am writing in a augmented form. So this is called augmented matrix. So we are considering those two vector as columns. We are putting, so 1 2 3 we have put So let me so I have put 1 2 3 in this column 1, and I put 0 1 2 in column 2. Okay, and this new checking element I'm putting it in augmented extra column. Okay, this is called augmented matrix. Now we can do row operations. So the first row operation will be R2 minus 2R1. So this will give me 1 0. First row is fixed. This is 0 1 B2 minus 2B1. Now to remove 3, we perform R3 minus 3R1. So 3 will get cancelled. It will give me 0. 2 minus 0, which is 2. And then B3 minus 3B1. Now again there is, we are trying to reduce in row reduced echelon form. So we need to cancel this 2 because leading entry 1 is already there in this column. So we'll cancel all those non-zero things. We'll try to cancel those things. So we'll perform R3 minus 2 times R2. First row is fixed, second row is fixed, third row is 0 0. Now this element will be B3 minus 3B1 minus 2 times this, right? 2 times B2 minus 2B1. So that will imply what will be the sum. So the system, let us calculate this sum. This is actually same as, what is this, minus 3B1 plus 4B1, which is same as B1, minus 2B2 plus B3. So the system has a solution if and only if. So when will this system have a solution? This is only possible if this 0 and this 0 are same. That is, this extra element should be 0. Otherwise 0 will be some non-zero element, which is not possible, right? The system has solution if and only if both sides are same. That is, those two rank are same. Rank of this matrix, if you know about rank of this matrix should be same as rank of the whole matrix. This is the necessary and sufficient condition to have solution. Okay, if you know about rank, then rank of A is same as rank of the augmented matrix. Augmented matrix denoted by this notation. Or if you don't know, then there is no issue. So the system has a solution if and only if this. So there is no combination 0x plus 0y. This should be same as some scalar. So this is, then that scalar must be same as this 0x plus 0y, which is 0, right? So this must be 0. This is the necessary and sufficient condition. So here this is actually b1 minus 2b2 2b2, yes, b1 minus 2b2 plus b3. So in this case b1 minus 2b2 plus b3 equal to 0. So let me put it aside. Okay, so the system has a solution if and only if this hold. So in our case, what was the vector? 3 1 2. So 3 minus 2 times 1 plus 3. So this is non-zero, right? So in our case, we are getting this is equal to same as 4, which is non-zero. Therefore, 3 minus 1, 3 1 comma 3 1 comma 2, sorry, this is actually 2. b3, value of b3 equal to 2. 3 1 comma 2, that does not belongs to this span. v1 v2. So let us review what we have done. We are checking that if this vector 3 1 2, this new vector, belongs to the span of those two earlier vectors. Okay. So I have said that to see this, we'll put those tuples as a column of augmented matrix. So first two will be those v1 v2, and the last one will be this new vector for which we are checking, and we'll try to reduce the corresponding matrix, corresponding augmented matrix. And if the rank of this one is same as rank of the augmented matrix, then it is okay. This element belongs to this spanning set of first two element. If not, then this tuple b1 b2 b3 does not belong to the span of those two vector. So this is what we have seen, that 3 1 2 does not satisfy this relation. This is non-zero, but left hand side it is 0. So this is not possible. So 3 1 2 does not belong to span of v1 v2. Okay. So using those kind of ideas, you can solve all the other questions which are remaining in these slides. So please try to solve those questions. And up to this, if there is any doubt or question, please feel free to ask. I believe there is no question. So let us stop here. Thank you for joining.
Thank you.
Thank you, sir.
Thank you.